This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 3303 solids. We're talking about torsion and power transmission. Power problems are really just a torsion problem. And we need to make a few definitions and relate the power to the torque. Power is defined as work per time, per unit of time. Work is torque, in this case, torque times the angle of rotation. It's force times distance. So power becomes torque times the angular velocity. I'll define those two terms there. In the SI system, the units of torque are Newton meters, and the units of angular velocity, omega, are radians per second, and therefore the units of power are, in the SI system, watts. 1 watt is equal to, by this formula T omega, 1 Newton meter per second. So it's involving revolution. In the US system, power, the basic units, foot-pounds per second, but we talk, for some reason, we've gotten into horsepower. 1 horsepower is defined as 550 foot-pounds per second. Power is equal to torque times angular velocity. So we're going to use that relationship. Plus, angular velocity is not normally thought of in radians per second. We think of frequency, which is the frequency of the shaft's rotation. F is revolutions per second under the formulas that we're going to use, which is cycle. 1 revolution is a cycle, cycles per second. So 1 revolution is 1 cycle per second is equal to 1 hertz. The frequency of that is considered to be 1 hertz. Because 1 revolution is equal to 1 cycle is equal to 2 pi radians all the way around the circle, then omega can be rewritten as 2 pi times the frequency, radians per second. So I can rewrite my power equation as power is equal to torque times angular velocity is also equal to 2 pi frequency times the torque. And so we're going to use this equation to calculate torque given power or something, and angular velocity or frequency. Then we're going to use the torsion formula, which we've been using. Tau is equal to Tc over J to design the shaft or check the shear stress in the shaft for given problems. So example 1 will work in the US system units. I have a motor here, and it's got a shaft connected to something it's driving, creating a torque. The motor develops 4 horsepower at 200 revolutions per minute. The find is figure out what the shaft diameter needs to be for a maximum shear stress of 15 ksi. So I know I want to get to torque. I want to figure out what torque is, and then I can work with that to figure out the shear stress and work backwards into a diameter for the shaft. So the first thing I look at is power is 4 horsepower, so that's 4 times 550, this number up here, foot-pounds per second. So I get 2200 foot-pounds per second. That's equal to the power, which is T, torque, times the angular velocity. Angular velocity is 200 revolutions per minute. That was given to me. There's 1 minute in 60 seconds, so I divide by 60, and I multiply by 2 pi radians per revolution to convert what's given here is 200 revolutions per minute. I want to get that into radians per second. So run the numbers and it works out to be 20.94 radians per second. So now I'm ready to go over here and figure torque from this formula. Power is equal to torque times angular velocity, so torque is equal to power divided by angular velocity. 2200 is my power, foot-pounds per second. 20.94 is my angular velocity, radians per second. I can see that I get 105.0 foot-pounds because I'm flipping this on the bottom, and seconds cancels out, and radians is dimensionless, so the units are correct at foot-pounds. Now I know enough to go back into my torsion formula. Tau max is TC over J, and I can rearrange that, and I can say tau max over T, which I know both of those numbers, 15 ksi, and the torque that I just computed up here, is equal to C, the radius, divided by J, the polar moment of inertia. Get my units all correct. I got 15 ksi is 15,000 psi, divided by 105 foot-pounds. I need to multiply by 12 to get it into inch-pounds to get my units correct. It's 11.90 inches cubed. Looking, I got pounds on inches, pounds per inches squared on the top, divided by pound inches, and that works out to be the pounds cancels out, and I get inches cubed on the top. Okay, so actually I get 1 over inches cubed. I've drawn that incorrectly because I've got inches over inches to the fourth are the units of that. So I'm going to rearrange that whole thing, and I better not confuse y'all. I need to make that 1 over inches to the cube, which is a weird concept. But anyway, that's equal to this formula C over J, which is C over pi over 2 times C to the fourth. The C cancels out one of the C's on the bottom, so I get 1 over pi over 2 C to the third. Rearrange that expression and set it equal to, or equate it to this, and I get that C cubed is equal to 1 over pi over 2 over times 11.90. Solving that, C cubed is equal to 0.05347. Cube root of that. Once again, I've got another error. That's the cube root. Cube root of that number is 0.376. That's the radius. So I multiply it by 2 to get my diameter. Just a little bit more than 3/4 of an inch. So that's the answer. Just need to look at what I know, what I don't know, and rearrange the equations and make sure my units are correct, and I can solve these power problems. Another example using the SI system and watts and meters and such. I have a motor driving a pump through a transmission shaft, and I say I have an 85 watt motor turning a 20 millimeter diameter shaft to the pump at 150 revolutions per minute. I want to find the maximum shear stress in the shaft. So go back up to my power equations. I know I have 85 Newton meters per second is my power, 85 watts. Up here, power is in the units of 1 Newton meter per second. So that's equal to torque times angular velocity. My angular velocity, I just need to convert this 150 revolutions per minute, sort of like I did up here, into radians per second. 150 divided by 60 times 2 pi is 15.71 radians per second. Now I can rearrange this power equation just to get torque is equal to power divided by angular velocity is 85,000, because I've got Newton meters, and I want to work in newtons and millimeters because I'm going for newtons per millimeter squared, megapascals. So I got 85,000 Newton millimeters per second, 15.71 radians per second. Do the math, I get 5411 Newton millimeters. That's my torque. Now I can go into my torsion equation. Tau max is TC over J. For a 20 millimeter diameter shaft, J is pi over 2 C to the fourth. C is the diameter, it's 10. I get 7854 millimeters to the fourth. Plug it into the torsion equation. T is 5411 Newton millimeters times 10 to convert it. Times 10 is my diameter, C, my radius, C, divided by 7854 J, polar moment of inertia. Checking my units, I got Newton millimeters times millimeters for my radius, divided by millimeters to the fourth, is equal to 6.89 Newton per millimeter squared, which is a megapascal, so that's my answer, 6.89 megapascals.